In order to tell if a table of values represents an exponential growth or decay function, I want to look for a common ratio. In other words, is there a number that I'm consistently multiplying by in my y values? If I have that, then I have exponential growth or decay. If I don't, then I don't. So taking a look at this first table of values, maybe I'll skip over that 2/3, but I can see that to go from 2 to 6, or to go to from 6 to 18, I'm multiplying by 3. And getting a calculator maybe to confirm this, I see that yes, that's true over here. 18 times 3 is 54. And also 2/3 times 3 is 2. So that's what I mean by having a common ratio. There's a consistent number that I'm multiplying by. And just side note, if you notice there's a consistent number you're dividing by, that's still an evidence of common ratio. However, don't think division, think multiplication. So for example, if you notice that you were dividing by 2 each time, really that's the same thing as multiplying by a half. You always want to look for multiplication when you do these. So to answer their first question, yes, this table of values does show exponential growth or decay. Since the numbers are getting bigger, I know that it's exponential growth. And my reason is because I see a common ratio. Okay, we'll come back to this in a second to write the equation. In my second table of values, again, I want to look for a pattern. And I do notice a pattern. To go from 15 or from 20 to 15, I'm subtracting 5, and I see that that's consistent all the way along the table. I'm subtracting 5, I'm subtracting 5, and I'm subtracting 5. Even though I find a pattern, that's not a common ratio. A common ratio needs to be a number that you're multiplying or dividing by. So this is not going to be exponential. In fact, it's just linear. There's the same number I'm adding or subtracting each time. So this one's not exponential. Going back to the problem we just did though, let's go ahead and write the equation of the exponential growth function we had. To do this, we could do it on a calculator, which we talked about in class. Otherwise, what I would recommend, the easiest way to do this, is just to remember what our basic exponential growth function looks like. The b value, our base, is going to be whatever our common ratio is. So in this case, I'm going to have y equals something times 3 to the x power. That a value then, sort of like slope-intercept form, is going to represent your initial value, your starting point. And when I say that, I mean when x is equal to 0. So you can think of it as your y-intercept. So if I know the y when x is 0, which I do this time, I'll have the a value. Okay, so the a value is where I begin my y-intercept. The 3 is my common ratio, and there is my exponential growth function. We can also do this using stat and then edit if you want to go ahead and enter your data into L1 and L2. And as we've done throughout the year, we'll be finding a regression for this. However, it's not a linear regression, it's not a quadratic regression. You'll look for an exponential regression. And if you go ahead and enter your data in and run that exponential regression, you'll see that we'll get an a value of 2 and a b value of 3 to write our equation. Make sure you do not multiply those numbers together. Order of operations says exponents come before we multiply, so this is definitely not equal to 6 to the x power. It's 2 times 3 to the x.